Thanks to CuriosityStream for supporting PBS Digital Studios. Since the discovery of the Higgs boson, physicists have searched and searched for any hint of new particles. That search has been fruitless, until perhaps now. Today on Spacetime Journal Club, we'll look at a paper that reports a compelling hint of a new particle outside the standard model, the sterile neutrino. Regular neutrinos are a bit aloof. They don't interact by the electromagnetic or strong nuclear forces, only by the weak nuclear force and gravity. They are so weakly interacting that they pass through matter like it isn't there. To have a 50-50 chance of stopping any given neutrino, you'd need a wall of lead 1 light-year thick. If regular neutrinos are aloof, then sterile neutrinos are complete loners. They don't even interact via the weak interaction. Even so, detection of a sterile neutrino would be incredibly important. Besides being the first expansion of the standard model family since the Higgs boson, sterile neutrinos are a candidate for dark matter, and their existence would have had a huge influence on the expansion of the early universe. We can detect regular neutrinos by watching for the rare interaction between a neutrino and an atomic nucleus in some huge volume of matter. An entire glacier in the ice cube experiment, or a huge vat of oil in the experiment we're about to discuss. Those regular neutrinos are spotted when they interact with matter via the weak nuclear force. So how on earth do you spot a sterile neutrino that doesn't even undergo that interaction? Well, by being extremely clever, obviously. This may have been achieved, as reported in the 2018 paper Observation of a Significant Excess of Electron-like Events in the Mini-Boon Short Baseline Neutrino Experiment. Catchy name. Before we get to that, we're going to need to go a few inception layers deep to set up the knowledge. We're going to drop through the standard model of particle physics, electric charge and antimatter, the bizarreness of quantum chirality and the Higgs mechanism, and finally, to why all of this points to sterile neutrinos. Hold on to your butts. First, the standard model of particle physics. As we'll see in upcoming episodes, these particles are divided into the bosons, which carry the fundamental forces, and the fermions, which comprise matter. The latter include the quarks, up-down, which comprise protons and neutrons, and the more exotic top, bottom, strange and charm, as well as the antimatter versions of these. And then there are the leptons, the ubiquitous electron and its heavier cousins, the muon and tauon, and again, each with its antimatter counterpart. Neutrinos are also leptons, and each of the heavier lepton flavors has a neutrino version. These have far lower mass, and unlike quarks and leptons, they have no electric charge, hence neutrino or little neutral one. Each flavor of neutrino also has an antimatter counterpart. So let's drop down into antimatter. An antimatter version of a particle has the same mass and the opposite electric charge. So an electron has a charge of -1 and an anti-electron has a charge of +1. Neutrinos don't have charge, so what's the difference between a neutrino and an antineutrino? Well, there's actually another property that gets reversed in antiparticles, and that brings us to the next level, chirality. The physical interpretation of chirality is pretty abstract. To explain, we need to start with helicity. Helicity is just the direction of a particle's spin relative to its direction of motion. Helicity can be right-handed, which means clockwise rotation, or left-handed, or anticlockwise. Like helicity, chirality can be left or right-handed, however the physical interpretation is much more abstract. It's related to the direction in which the particle's phase shifts under rotations. Helicity depends on your own motion relative to the particle in question. It flips direction if you start moving faster than the particle. However, chirality is fundamental to the particle and doesn't depend on your own velocity. This is where we need to expand our picture of the particles of the standard model a little and open up the possibility of the sterile neutrino's existence. There are actually two versions of each fermion, one with right-handed chirality and one with left, and that's on top of the matter-antimatter split. As we saw in our episode on the Higgs mechanism, real quarks and electrons are actually a combination of left and right chiral particles that oscillate back and forth between those particles through interactions with the Higgs field. That oscillation is what gives these particles their mass. Still with me? Good. Like electric charge, chirality is also reversed in antimatter. For example, both left and right chiral or negatively charged electrons have their own positively charged antimatter particles, which are right and left chiral respectively. These different chiralities are thought of as completely separate particles, and there's a good reason for this. Chirality determines whether a particle can interact with the weak nuclear force. The left chiral electron feels this force, and the right chiral electron does not. This interaction is flipped for antimatter. The right chiral anti-electron feels the weak force, while the left chiral anti-electron does not. Okay, got all of that? We're finally ready to bring it back to neutrinos. Every neutrino we've ever observed was spotted due to the weak interaction. That means we've only ever seen left-handed neutrinos or right-handed antineutrinos. The opposite chirality, right-handed neutrinos or left-handed antineutrinos, should only interact gravitationally, so it would be near impossible to detect. These are the sterile neutrinos. They aren't part of the standard model because until now we had no concrete evidence that they exist. But there's good reason to suspect their existence. If neutrinos gain their mass by the same mechanism as quarks and electrons, that means their chirality oscillates. That would require regular left-handed neutrinos to spend at least a bit of their time as sterile right-handed neutrinos. Now, we know that neutrinos have mass due to a completely different type of oscillation. We've observed a neutrino's flavor can change. Electron neutrinos can become muon neutrinos, can become tau neutrinos. In order to evolve that way, neutrinos must experience the flow of time, which means they can't be moving at the speed of light, which means they must have mass. That mass may indicate the existence of the sterile neutrino, but it could also come from some more exotic mechanism. For example, the Majorana mechanism that would require the neutrino to be its own antiparticle and would break the standard model even more than the existence of the sterile neutrino. Okay, let's get to the experiment. Mini-Boon is an experiment at Fermilab in Illinois. Neutrinos are created by colliding protons together to produce a beam of mostly muon neutrinos. These then travel to a 800-ton vat of mineral oil. Rare interactions with nuclei in the oil reveal the nature of the neutrinos. Now, the evidence for sterile neutrinos is subtle, and they certainly weren't directly detected. Instead, Mini-Boon detected way more electron neutrinos than expected. So I told you that neutrinos oscillate between type, electron, muon, tau. So the Mini-Boon experiment starts with muon neutrinos, and some of these transform into electron neutrinos by the time they hit the vat. According to the standard model, that oscillation should be extremely rare over the very tiny distance of the neutrino beam. A lot more muon neutrinos made the transition to electron neutrino than was expected according to the basic standard model. But one way to speed up that transition is to introduce sterile neutrinos as an intermediate step in the oscillation. If muon neutrinos can flip their chirality and become sterile neutrinos, then it's an easier transition from sterile neutrino to electron neutrino, and that's a proposed explanation of the Mini-Boon team. The team finds an overabundance in electron neutrinos at the 4.8 sigma level. Now that's actually slightly below the critical 5 sigma level required for claiming a high confidence detection. However, Mini-Boon then combined their results with that of an older experiment that has also detected a hint of this excess. That was the Liquid Scintillator Neutrino Detector, LSND, experiment at Los Alamos, which in 2001 published a 3.8 sigma excess in electron neutrinos. Combined with the 4.8 sigma Mini-Boon result, the authors claim a 6.1 sigma signal, which would be considered extremely significant. If this is right, then it's the first particle outside the standard model since the Higgs boson. And if we really have seen the influence of the sterile neutrino, we now know something about it. It would have a relatively low mass, at around 1 electron volt. Forgive the particle physics energy units for mass. That's heavier than regular neutrinos, but way too light to be a candidate for dark matter. Okay, I know you're excited, but don't crack the champagne bottle yet. This result is in conflict with some other measurements. The Ice Cube neutrino detector in Antarctica has found no evidence of the existence of sterile neutrinos based on the transition of muon to electron neutrinos as they travel through the body of the Earth. An analysis of the cosmic microwave background radiation by the Planck satellite shows that the early rate of expansion of the universe is consistent with only 3 neutrino types. Add more neutrino types, like the sterile neutrino, and the early universe would have expanded faster. There's an interesting conflict here. The mini-boon result looks compelling. Hopefully it isn't some sort of experimental error, which it might be. Remember those faster than light neutrinos? Yeah, we don't talk about that anymore. If this one is real, then something is missing in our understanding of physics, and glitches between experiment and theory are exactly how new physics gets discovered. The sterile neutrino may have been discovered, or we may have just spotted something even more interesting. Either way, we'll have peered just a little deeper into the fundamental building blocks of spacetime. Thank you to CuriosityStream for supporting PBS Digital Studios. CuriosityStream is a subscription streaming service that offers documentaries and non-fiction titles from a variety of filmmakers, including CuriosityStream originals. You can get the first 60 days free if you sign up at curiositystream.com/spacetime and use the code spacetime during the sign-up process. In the last 2 episodes, we covered the black hole information paradox and asteroid mining. Today, we're going to cover your questions from both. OI Snowy asks about a statement I made in the information paradox episode. With perfect knowledge of the current universe, it should be possible to perfectly trace the universe backwards and forwards in time. So how does that work with the cosmic event horizon? Shouldn't regions outside the event horizon be lost to our access and therefore impossible to trace backwards? Well, sure, absolutely. The statement about the retraceability of the universe doesn't actually care about event horizons, whether cosmic or black hole. The idea is that if the information is still existent somewhere, then the universe could be put in rewind and it would end up back where it started. Even a black hole should unravel in that case. But if information is actually destroyed, then the rewind would get stuck at the point of information destruction because the universe wouldn't know which of multiple possible histories it led to that point. But you're absolutely right in thinking that we can't have perfect knowledge of the universe. We also can't rewind the universe, so this is just a thought experiment. A few of you wonder whether adding extra mass to Earth from asteroid mining could lead to problems, like with our orbit or Earth's gravitational pull. So Earth is around 2,000 times more massive than the entire asteroid belt. Even if the entire belt were brought to Earth, you wouldn't notice the difference in gravity. And no one's proposing we do that, only the very tiny fraction of precious and rare earth elements are likely to be profitable to bring back to Earth. Some of you also wondered whether mining the moon could be more efficient than mining the asteroid belt. Well, the moon is definitely an option for mining, and it's going to have some useful heavy elements from crashed asteroids. It's not clear that it's better than near-Earth asteroids. To get stuff off the moon, you have to contend with its admittedly low gravitational field, compared to essentially no such field in the case of asteroids. Also, mining the moon is going to have a lot of political complications compared to asteroids. For one thing, our moon is protected from exploitation by the Outer Space Treaty, which prohibits nations from claiming any sovereignty there. Asteroids, however, are fair game. Lisa Vaught likes this channel because when she repeats this stuff to her friends, they're like, "Damn dude, how'd you get so smart?" Weird thing, that's actually how I got started. One minute I'm learning the constellations or Einstein quotes to impress my friends, and next, well, it's a long, sad down spiral to where I am today. I heard of this one guy, he started out memorizing pi to impress chicks, ended up inventing the atomic bomb. People, this stuff may be fun at parties, but please, everyone, nerd responsibly.